Hello everybody, welcome back to Calculus 1 online at Frederick Community College. In this video we will discuss the limit laws. Let me give you a quick outline of what we're going to do in today's lecture. First, we will talk about the basic limit laws and rules, and I think you will find this topic fairly intuitive. Then we will discuss problems where we use these laws in order to evaluate limits. Then we will talk about problems where we cannot apply the basic laws. So how do we approach those? We will talk about two techniques. One is factoring, and the other one would be multiplication by conjugates. Then we'll switch our focus to computing one-sided limits, something we have already done in our previous lecture, and then we will finish off today's lecture with talking about limits of piecewise defined functions. So here on the right side of the slide, you can see an example of a piecewise defined function where for one portion of the domain, the function is acting one way. So here, for example, we have a parabola that's opening down, and that is for one portion of the domain, and that's from negative infinity to 0, right? And then for the second portion of the domain, from 0 to positive infinity, we have a straight line, okay? So that's just one example of what piecewise defined functions might look like. Now let's go ahead and review the two basic limits that will be foundation for evaluating many limits in this class. So here we have two expressions. The one on the left says the limit of x as x approaches a is equal to a. And the one on the right says the limit as x approaches a of c is equal to c, where c is some fixed constant. Okay, so these might seem fairly obvious to you, and that is perfectly fine, but let's go ahead and take a look at the graphs and see what these limits would look like if we were to look at the functions in their graphs. So let's start with the one on the left. So here we have x as the function, and that is just the identity function, right? So that's what it looks like. Okay, it's just a straight line that goes through the origin with the slope 1. So of course it makes sense that if we fix a, could be anything, but let's say a is equal to 1, then as we're approaching 1 from either direction, okay, what is going to be our limit? The limit will be the same value as x is approaching because the function is the identity function. Okay, so that's your graphical representation of this limit. All right, let's take a look at the second limit. Here, c is some fixed constant. Okay, what is that going to look like? It's just going to be a straight line that's a horizontal line. So in my case, I picked c to be 3. Okay, and it makes sense that if I fix my a, so let's say a in this case is 2, okay, and if I'm approaching 2 from either direction, okay, it doesn't matter which direction I'm coming from, or it doesn't even matter what a is, the limit will always be that number. Okay, so graphically, that's what these two limits are telling us, and we will use these, even though not explicitly. We will be using these rules in evaluating many other limits in this course. Now, let's go ahead and discuss the limit laws that are a little bit more involved. So here we have two functions, let's say f and g, that are defined for all x not equal to a over some open interval containing a. This is just a rigorous part of these rules, not necessarily something that you need to memorize. Okay, and suppose the limits for each individual function exist, right? So here is the limit of f as x goes to a, and that's equal to some number L, and then the limit of g as x goes to a, and that's equal to some number m. Okay, and c is a constant. That is the notation that's commonly used in this course. Then we can establish the following rules. Okay, we have sum law, and that is we can distribute the limit through the sum right here. Okay, so if you are considering the function f plus g, then the limit of that function as x goes to a is just the sum of the limits of individual functions. Similar rule applies to subtraction. So this is basically saying that we can distribute limit through the difference of two functions, and it is equal to the difference of the limits. Okay, constant multiple law for limits. This one is saying that if you have c times the function, you can pull this constant up front, and then the result will be just c times L. Okay, then the product law for limits says that if we have a product over here inside the limit, okay, then we can distribute this as the product of two limits. So that turns out to be L times M. Okay, then the next rule says quotient law for limits. If we have a division of two functions and we would like to find the limit of this quotient, then we can just take the quotient of the limits as long as the denominator is not equal to 0, right? So as long as the limit as x goes to a of g is not equal to 0. All right, and then the power law for limits says that if we have power over here, then we can just take the limit of the function and then take that number, raise it to this power. So that's your L to the n. And then the last one is the one that's dealing with radicals. Okay, so root law says that if you have a radical over here, then you can also take it out. Okay, and that would be the nth root of L for all L if n is odd. Now, if n is even, we just need to make sure that this expression is greater than or equal to 0. Okay, so these are the rules that we will be using in today's lecture. All right, you don't need to memorize them. You don't need to recite them. You will just need to know how to apply them. All right, now that we've discussed these rules, let's go ahead and talk about a series of problems where we will be applying the rules to compute limits. You will notice that I wrote out all my solutions by hand, and I did that to demonstrate what your solutions should look like when you're working on your exams and quizzes. So let's go ahead and review each solution one problem at a time. Okay, so for the first one, I have limit as x goes to 0 of the expression 3x cubed minus 2x plus 5. And here is my solution. The first step that I did was to break down this as a sum of 3 limits. So that's one of the first few rules that we've discussed on the previous slide. Okay, and then on the second step, I took out 3, pulled it up front, and also -2 over here for the second expression. And then the limit of a constant is just that constant right here. So that's one of the basic rules we've discussed early in the lecture. Okay. And after that, we just need to evaluate the limit. Okay, so what happens to x cubed as we approach 0? Of course, that's 0, and that's where that number comes from. What happens to x as x goes to 0? That is your identity function. So same thing, this is 0 right here. And then once we carefully compute this, we're going to get 5. Okay, so that is the answer for this limit. And you might be wondering, well, could we just plug in 0 for x into this expression? And the answer is yes, absolutely. Okay, and you don't need to necessarily write out all of these details, but I wanted to demonstrate the rules. Okay, so this particular solution is provided to show you that we are applying all the rules that we've discussed. We might not just be explicitly writing it out. Okay, so 5 is the answer for the first problem. Let's take a look at problem number 2. Here I have a rational expression. So I have a quotient, right, of two functions, 2x squared minus 4x in the numerator, and then 3x minus 7 in the denominator. So the only thing that I need to check is if I plug in 1 in here, what do I get? Okay, 3 times 1 minus 7, that's going to be negative 4, which is not equal to 0. And that's great. So now I can apply the quotient rule. And here I'm writing out my solution. So I wrote everything as a quotient of two limits. Okay, and now I can just plug in 1 for x everywhere I see it on top and bottom, and then carefully compute. So we get 1/2 as the answer. All right, so notice that over here, I kind of skipped the step of distributing the limit through my differences and taking out the constant. Yeah, you can skip that step. We don't need to break it completely down. Of course, you can if that makes it easier for you to see what's going on. All right, but if you want to skip that step, that is completely fine. Okay, so problem 3, what do we have here? We have a radical expression. We have limit as x goes to -3 of the root x squared minus 3x plus 1. Okay, so for this root, we need to make sure that this expression under the radical is greater than or equal to 0. Otherwise, we have an undefined expression. Okay, so if I plug that in, what am I going to get? Let's see, -3 squared minus 3 times -3 plus 1, that is certainly greater than 0. Okay, and here is the full solution. So I'm going to evaluate that expression. It's going to be positive 19. So the final answer is root 19. Okay, so let me write this over here. This is square root of 19. And for the second problem, the answer is 1/2, right? Okay, and then the last problem for this slide would be the limit as x goes to 2 of the expression -4x plus 3. Okay, so you might be tempted to multiply this power through. We don't need to. Recall that we can apply the power rule. All right, so how do we do this? I'm going to write it as limit of -4x plus 3 as x goes to 2 raised to the second power. So I kind of took that power out. And now I'm going to evaluate my expression at 2 and then raise that to second power. So we get what? We get -8 plus 3, that's -5 squared. That would give us 25. Okay, so this is 25. All right, so these are your first few examples where we evaluate the limits using all the rules that we've discussed, even though we don't necessarily have to kind of break it down to all the details. Okay, if you see that you can just evaluate this expression without having things like, you know, division by 0 or negative number under the radical, then you're good to go. Let's take a look at the next set of limits. Here we would like to evaluate limits of exponential functions. And the nice thing about exponential functions is that if we're working with basic exponential functions, the domain of those is all real numbers. So all we have to do is just evaluate our limits for the given value of a. Okay, so the first problem says limit as x goes to 2 of the following expression, e to the power 3x minus x squared. Okay, here is my solution. All we have to do is plug in 2 for x everywhere we see it, and we get e to the power 6 minus 4, which is just e squared. Okay, and you leave it as is. You do not need to approximate this number. All right. In fact, I encourage you to just keep it in the exact form. So that is your answer right here. Okay, let's take a look at the second problem here. Our base is 10. Okay, this is still an exponential function. It's just our base is something different than e. So the function is 10 to the power x minus 1/2, and we would like to find the limit as x goes to 1. Same idea. We're just going to evaluate that expression at x is equal to 1. So we plug in 1 here, and that's going to be 10 raised to the power 0.5 or 1/2, and that's equivalent to saying square root of 10. Okay, this is fairly straightforward. And then the last example, here we have a slightly different setup. We still have an exponential, but it is shifted, right? So notice that -1 is outside of the exponent, right? It is not in the exponent. Okay, so all right, let's take a look what's going on here. This is the limit as x goes to 4 of the function e raised to the power 0.5 x minus 2, and then minus 1. Okay, how do we do this? Same idea, we're going to carefully evaluate it. So I'm plugging in 4 for x. Okay, so that's over here. And that's, of course, going to be just 0. E to the 0 is 1. So the final answer is 1 minus 1, which is 0. All right, so this is a quick review of exponentials, and you can see that when we evaluate exponential functions, it is pretty straightforward to evaluate these limits. The next set of problems will involve limits of logarithmic functions. Okay, so here you have 3 examples. Let's go ahead and review them one at a time. Okay, the first one says limit as x goes to 2 of the expression log of 4x plus 2. Okay, so when evaluating limits, we need to be careful with logs and make sure that the expression inside the log is greater than 0, right? We want to make sure this is greater than 0 when we evaluate it at the given value of a. Okay, so in this case, a is equal to 2. So if I plug that in into our expression 4x plus 2, it is clear that we're going to get something bigger than 0. So that's all we have to do. We're going to evaluate it. Okay, so this is log of 4 times 2 plus 2, which is log of 10. And if you recall, log without base being mentioned, okay, it is automatically base 10. So the final answer is just 1, right? So log base 10 of 10 is just 1, right? So you can think about it as what power should I raise 10 to get 10? And of course, that's just the first power. Okay, so that's that. Let's take a look at the second example. Here we would like to find the limit as x goes to 3 of log base 9 of x. Okay, so now I'm looking at this expression right here. This needs to be strictly greater than 0 if I plug in 3, and of course it is. Okay, 3 is greater than 0, so we just need to evaluate this function. All right, so log base 9 of 3, okay, that is 1/2. Okay, why is that? Recall how logarithm works. So 9 raised to the 1/2 power is indeed 3, right? So square root of 9 is 3. So that's true. Okay, so the answer for this limit would be just 1/2. Okay, what about the last example? So the third example is limit as x goes to 2 of log base 5, and the expression inside the parentheses is x minus 1. Again, remember this needs to be greater than 0, okay? And if I plug in 2 for x, we do get something that's greater than 0. Okay, let's see the solution. So this would be log base 5 of 2 minus 1, which of course is equal to 1. And that is log base 5 of 1, and that is 0. Recall how we do this. 5 raised to what power gives us 1? And of course, that's just 0. Okay, so 5 raised to this power of 0. Does that give us 1? Yes. Okay, so that's it. So these examples will give you a quick review of some of the log properties, right? Okay. Let's take a look at some problems where we would like to evaluate limits of trigonometric functions. Now, this will be a nice review of trig functions, their domains, and some of the table values. And I would like for you to keep in mind that when we're working with trig functions, we need to remember that some of them are undefined for certain values of x. Okay, so let's go ahead and start with the first one. This one says limit as x goes to 0 of the expression 1 plus 2 cosine x. Now, cosine x is defined for all values of x, so there is no issue here. We can just go ahead and evaluate it. So this will be 1 plus 2 cosine of 0. We know that cosine of 0 is just 1, so the final answer is 3. Okay, let's take a look at the second problem. Here we have the limit as x goes to pi over 4 of the expression 2 cosine x over sine x. Now, both cosine and sine are defined for all values of x. However, sine here is in the denominator, so we need to be careful. So this is the case where we say, okay, what is our x approaching? Is it approaching one of the values where sine is going to be 0? And for this particular problem, the answer is no. X is going to pi over 4, and sine is non-zero there, right? We know what that value is. This is one of the standard values from the unit circle. Okay, so this turns out to be what? This is just 2 cosine of pi over 4 over sine of pi over 4. We can do that because now we know denominator is not 0. Okay, and we get the same value. This is 45 degrees, right? So sine and cosine are the same there. Of course, that cancels out, and the final answer is nice. It is just 2. Okay, let's take a look at the last example here. So problem 3 says, what is the limit as x goes to pi of the expression 1 plus tangent x over 1 minus tangent x? So again, here we need to pause and think about it for just a second. Tangent is undefined for infinitely many points, okay, for infinitely many values of x. However, pi is not one of them. Okay, a tangent of pi is 0, and when we plug that in here, in particular in the denominator, we just get 1 minus 0, which is 1, and that is not equal to 0, and that is what we want. Okay, so let's go ahead and plug that in. We're going to plug in pi for x, so we get 1 plus tangent of pi over 1 minus tangent of pi, and that of course turns out to be 1. Okay, so these examples are set up in such a way that we can just evaluate our functions at these values. Okay, at some point we will consider problems where we will have division by 0 or maybe 0 over 0, but that's a little bit further, that's a little bit later in the semester. Okay, but it's always important to double check the domain of your functions and make sure that we don't have 0 in the denominator. Okay, the next set of problems will involve polynomials and rational functions. So here you have a rule that says if we're working with polynomial functions, then you can just evaluate that polynomial at the value of a. Okay, that's something that we have already done at the very beginning of the lecture. And then if you're working with rational functions, right? So it's polynomial on top divided by the polynomial on the bottom. We can also just evaluate this quotient as long as q, the polynomial on the bottom, is not equal to 0. Okay, so let's take a look at the first 3 examples. All right, so the first one says limit as x goes to 1 of the polynomial function 3x squared minus 4x plus 5. Okay, by this rule, we can just plug in 1 for x. And when we do this, we get 3 times 1 squared minus 4 times 1 plus 5. The answer is 4. Okay, so we had a similar example at the very beginning of the class where I broke it down, right? So we don't need to do that. We can just plug that in into the polynomial. Okay, let's take a look at the second example. So this one is done. Here we have limit as x goes to 3 of the function 2x plus 1 over x squared minus 4. Okay, so whenever we're working with rational functions, we want to focus on the denominator. So here I have x squared minus 4. If I plug in 3 for x, what do we get? We get 9 minus 4, which is non-zero. Okay? All right, so that's all we need to do in order to proceed. Okay, so we plug in 3 for x. So we get 7 on top, 5 on the bottom. The final answer is just that, 7 over 5. All right, and then the last problem, same idea. We have limit as x goes to 0 of the rational function x squared minus 4 over 2x plus 10. So I'm going to kind of zoom in on the denominator, 2x plus 10. If I evaluate that expression at 0, I do not get 0. And that's all we need to do to check and proceed. So I'm plugging in x, 0 for x, and we get negative 4 over 10. And that of course reduces to negative 2 over 5. All right, so that is our answer here. Okay, so polynomials are nice because when we're finding the limits of those, we just plug in our value into the polynomial. And then rational functions are also nice as long as the denominator is not equal to 0. Now you might be wondering, what do we do when we get 0 in the denominator? So that is something that we're going to discuss on the next slide. Now we're ready to discuss the technique of factoring when evaluating limits of rational functions. So let's take a look at these 2 examples. First one says, let's compute the limit as x goes to 4 of the rational function x squared minus 16 over x minus 4. Now notice that if we plug in 4 for x, we're going to get the following. We're going to get 0 over 0, which is what we're going to refer to as one of the indeterminate forms. And this form at this stage of the class will basically tell us that we need to do some algebraic steps in order to evaluate this limit. Now, later in the semester, once we know what derivatives are, we're going to approach this same problem slightly differently, and we're going to get exactly the same result. But for now, we're going to be applying the method of factoring. So anytime I get 0 over 0, that's what we need to focus on. We need to factor the top and the bottom as much as we can. So what do we do here? Well, the bottom is already factored, okay? But on the top, we have difference of perfect squares, and that factors as x minus 4 times x plus 4. And what happens here? we get this factor, that's a common factor, x minus 4, that cancels out. And now we get limit as x goes to 4 of just the expression x plus 4. Okay, and that's nice because we can just evaluate that and we get 8 as our final answer. Okay, so what do we call this number right here? X equal to 4. What we're going to call it? We're going to call it removable discontinuity. Okay, and that's what happens when we have a common factor in a rational function. And then if you were to graph this function right here, the original one, so let me go ahead and highlight it. If you were to graph this function, x squared minus 16 over x minus 4, it's actually just going to be a straight line with a hole, okay, at x is equal to 4. All right, you can check it. You can graph it using Desmos. Okay, so that's your first example. Let's take a look at a similar example. All right, so limit as x goes to 3 of the rational expression x squared minus 3x over 2x squared minus 5x minus 3. Again, if I were to plug in 3 for x, we're going to get 0 over 0. Okay, you can check the arithmetics here, and you'll see that that's what we get. So 0 over 0, let me go ahead and emphasize that this is not equal to 0. No, this is an indeterminate form, okay, that at this stage of the class tells us, okay, you got to do some algebra here. All right, so I'm looking at the top and the bottom of this function. Both of them can be factored, right? So here is my solution. So we factor x on the top, so this becomes x times x minus 3. And on the bottom, we have 2x plus 1 times x minus 3. And notice that we do get a common factor. Okay, so x minus 3 cancels. Okay, that's our removable discontinuity. And now we have a nice expression x over 2x plus 1, which we can evaluate at 3. Okay, so now we just plug in 3 for x and we compute that limit. So that turns out to be 3 over 7. Okay, so factoring is a nice technique, the one that we're going to apply to the limits whenever we are working with a rational function and we get the form 0 over 0. Let's review the next technique for evaluating limits, and that is multiplication by conjugates. We're going to take a look at these two problems. For the first one, we have the limit as x goes to -1 of the expression square root of x plus 2 minus 1 over x plus 1. So how do we approach this problem? First, we're going to plug in -1 everywhere we see x. And once again, what we get here is a form 0 over 0, which means we need to apply some algebraic technique. And the technique here is to multiply top and bottom of our fraction by the conjugate of this expression that contains the radical. And what is the conjugate? It is that same expression, except we're changing this sign right here. If this is minus, we're changing it to a plus. And if this was a sum, we would change it to the subtraction. Okay, so notice what happens here. We get square root of x plus 2 plus 1. Okay, we're multiplying the top of this fraction by this sum, and that's what the conjugate refers to. This is the conjugate. And also we have to do the same thing for the bottom in order to preserve our expression, right? So we're really just multiplying by 1. And the reason why we do this is the following. So we know that if we do a minus b times a plus b, we know that if we multiply this through and combine like terms, we're going to get a squared minus b squared, right? So this is the difference of perfect squares. And this is very useful when we would like to get rid of that radical, right? So in this case, that's square root of x plus 2. So once we follow all the algebraic steps, we get the following expression right here. And notice that x plus 2 minus 1, that's just x minus 1, then these expressions cancel out. And that's the whole idea here. When you multiply your function by the conjugate, if we do it carefully, we're going to get cancellation of that term that causes that 0 in the denominator. All right, so once we do this, we get the following expression right here, and we can evaluate this at -1. So the limit, as x goes to -1 of our original function, we evaluate now this reduced function at -1, and it's just 1/2, right? So that is what the limit here is. Okay, so now let's take a look at a similar problem. Here we have limit as x goes to 5 of the expression square root of x minus 1 minus 2 over x minus 5. Okay, similar idea. First, we're going to evaluate this at 5. So we'll plug in 5 for x. And once again, we get 0 over 0. So this is our hint that we need to apply some algebraic step. Okay, what is the conjugate of this expression? So that would be square root of x minus 1 plus 2. So notice this is the sign that we're changing. Okay, not this one, not the negative inside the radical, right? So it is whatever the outside is. Okay, so we multiply this through, we get difference of perfect squares on top. So that's nice, because now we can see that this is equal to x minus 5, which cancels out with the factor on the bottom. Okay, and that's why I keep this expression as is. I'm not going to multiply it through because one of the factors cancels out. Okay, so once again, we get a slightly different expression, but now we can evaluate this at 5. Okay, no problem here. There is no 0 in the denominator. So the final answer for this particular question is 1/4. All right, so to just summarize, how do we approach these problems? First, evaluate your function at that value of a, right? So whatever x is approaching. If you get 0 over 0 and you have an expression that contains a radical, the trick is to multiply both top and bottom by the conjugate. Do the simplification, carefully multiply everything through. At some point, you will have cancellation. And once that's done, you can evaluate your limit at that number, and it will be a nice answer. Let's take a look at some problems where we're evaluating one-sided limits by looking at graphs of functions. First, we have the square root of x minus 5. That's our function that we're going to review. And we would like to compute both left and right limits as x goes to 5. Let's go ahead and start with the right limit. So we can see that as x approaches 5 from the right side, the graph of the function is getting closer and closer to the x-axis, and that's where it's going to obtain the value of 0. So the limit, the right limit of this function is 0. And algebraically, you can think about it as if we plug in numbers that are close to 5 by just a little bit bigger than 5. So let's say something like 5.001. We can compute that difference and then take the square root. It will be a small number, and that number gets closer and closer to 0 as x gets closer and closer to 5. Okay, so there are two ways to think about it. You can just look at the graph, and you could also think about it in algebraic terms. Okay, now what happens to the left limit? As we are approaching x is equal to 5 on the left side, notice that there's no graph in this portion, okay, of the plane. So what does that mean? Well, the function is not defined for values that are less than 5, okay? So we would say the limit here does not exist. Does not exist. Okay, and one way to think about it is this. Let's say we plug in something that's less than 5 over here. Could be any number, let's say 4.9. If we do 4.9 minus 5, that will give us a negative number. We cannot take the square root of that value since we are dealing with real numbers and not complex numbers. So the function is undefined on that interval from negative infinity to positive 5, not including, which means the left limit does not exist. Okay, let's take a look at the next problem. Here we are dealing with a trig function, so tangent of x. We know that this function is periodic, but here I'm just graphing it on a bounded interval. Okay, and we would like to compute the limit as x goes to pi over 2 from the right and from the left and see what happens. Let's start with the right limit. Okay, so as we are approaching x is equal to pi over 2 on the right side, right? So you can think about it as plugging in numbers that are a little bit bigger than pi over 2. We see that our branch is going down to infinity, what happens here? So this is going down to infinity. How do we denote that? We say that the limit is negative infinity. Okay, all right. How do we think about it in algebraic terms? Remember that tangent is sine over cosine. Let me go ahead and write it up over here. So sine of x over cosine of x. So one way to explain this is to take a look at what happens to sine and cosine once x goes to pi over 2 from the right. So that's values that are a little bit bigger than pi over 2. You can think about it as angles in second quadrant. Well, we know what happens to sine, so this would be going to 1, right? So pi over 2, 90 degrees, that's where sine is equal to 1. What about cosine? Well, we know that cosine of pi over 2 is 0, right? But what happens to cosine as x is approaching pi over 2 from the right? You can think about it as small negative number. Okay, small negative number, and what we're essentially doing, we're taking 1 and dividing by a small negative number, and that's how we get negative infinity. Okay, so that's the algebraic explanation. Let's take a look at the left limit. What happens here? So as we are approaching pi over 2 on the left, that would be values that are in first quadrant, right? So angle that's close to 90 degrees, but it's smaller than 90 degrees, right? Okay, so what happens here? We can see that the branch is going up to infinity. We're going to say that the limit here is positive infinity. Okay, you can just write infinity. That assumes that it's positive. If you want to emphasize that it's positive infinity, you could put a positive sign in front of it. All right, same idea. We know that sine of pi over 2 is 1. What happens to cosine as we approach pi over 2 from the left? This time values that are in first quadrant, right? So cosine there is positive, so we do 1 over a very, very small number that's positive. That's why we get positive infinity. Okay, so here are your examples where you evaluate limits, one-sided limits, by looking at the function's graph. And of course, you can explain your reasoning using algebraic terms. Let's take a look at the next set of examples where we're working with limits of piecewise defined functions. So the first function is f of x that's defined to be parabola x squared on the interval from -infinity to +3, including the 3. And you can see the graph of that function over here. And then it is a straight line x plus 4 on the other portion, so for x greater than 3. And notice that for the first portion where x is less than or equal to 3, we have a solid dot over here. Okay, and then when x is strictly greater than 3, we have a hollow dot. Okay, that's important to know. All right, so now how do we compute the limits? We just look at the graph, and we can also compute it algebraically. Well, if looking at the graph, the left limit would be what? As we're approaching 3 from the left side, looks like we're going to 9. Okay, and then as we're approaching 3 from the right side, looks like the graph is going to 7. So algebraically, all we have to do is plug in 3 into the correct portion. So from the left side, I'm plugging it into the quadratic. So just squaring 3. That gives us 9. And the right limit, I'm plugging it into the second portion of the function, 3 plus 4, and that equals to 7. Let's take a look at our last example for today's lecture. Here we have a function h of x that's defined to be x squared minus 2x plus 1 for the interval x less than 2. So that's from -infinity to +2, not including the 2. And then it's a straight line for x greater than or equal to 2. Okay, so how do we compute our one-sided limits? As we approach 2 from the left, what happens to our graph? Looks like it is going to 1. And the same thing happens as we approach 2 from the right side. Notice that even though these two parts of the graph are different, right? One is a quadratic function, another one is a linear. They do go to the same point. So that would be 1 right here. And of course, we can check this algebraically as we plug in 2 for x in each of the equations. We get 1 in each case. All right, so you might have noticed that this problem is slightly different from the one that we've discussed on the previous slide. There is no gap in the graph here, and that's going to be important to recognize for problems where we asked about continuity, which will be our next section. Okay, so this is where I'm going to stop this lecture. Thank you all for watching, and I will talk to you next time.